Perfect squares. Do we remember our perfect squares?
Yeah. Yes.
Okay, what are the? Do we remember the first 14 of them?
Almost.
Yeah.
Well, the first one's 1. Then what's the next one?
1.
Okay, we start with 1. What's the second perfect square?
4.
Okay.
9.
16.
25. 36. 49.
Okay, Ben's on a roll.
81.
There's a 1 in between.
He doesn't.
81. Is that one? Oh, I got one. I'm part of
100.
it.
100.
I'm part of it.
Okay, now it gets hard.
121. 121.
144.
144.
Oh my gosh, you guys.
2 more. 2 more. 169.
That was me.
There we go. What's the 15th? Do you remember? 225. Yeah. 225. Late tell. Nice job. When we simplify radicals, we're going to be using these guys quite often. When we're simplifying radicals, radicals being square roots, as a remember, a radical sign is a square root sign. We're simplifying square roots. We're going to write these. We're going to rewrite so that 1, there are no perfect squares, factors, under the radical. Do 2 things. First, we're going to write it so there are no perfect square factors under the radical. None of these could get multiplied evenly into the numbers that are there. And also, we want no radicals under a fraction bar, or no radicals in the denominator of a fraction. As we go through, let's find some perfect squares that go into each of these. And let's rewrite these as something times that perfect square. So what's a perfect square that goes into 800? We just listed 14 of them. What's the largest perfect square that goes into 800?
100.
100. So let's rewrite 800 as 100 times something. Okay. If we, by doing this property of radicals, so that you can break them into what are called by their products. So if we're multiplying, then we could rewrite this as an intermediate step as square root of 100 times the square root of 8. And what's the square root of 100? It's the 10th perfect square, so it should be 10. 10 roots of 8. Oh boy, this is actually not done yet. Because I think there's a perfect square that goes into something under this radical. 2. So it's 10 times the square root of 4 times 2. So this is what? 10 times 2 times root 2, square root of 4 being 2. So what is this the best written as?
12. Oh, 10 times 2.
20 roots of 2. There are no more perfect squares other than 1 that goes into here. And there's no radicals in the denominator. This is our best answer. Square root of 800 is best written as 20 roots of 2. How about a perfect square that goes into 60?
7.
7 times 7 is 49. Does 49 go into 60 evenly? No.
4.
4. What's 4 times 4? Well, 4 goes into here. I bet you 16 goes into there as well. 60 is the same as 16 times 5. Is the largest perfect square that goes into 60. Square root of 16 is 4. We don't know the square root of 5, so what is it? Well, is that 7? Oh. 80. Oh, excuse me. Okay, we'll go with 4 then. Fine. What? No, it's a different one.
No, 12 times 5
It's 12. Okay, you're wrong.
Maybe we do 4 times 3 times 5.
4. Okay, I guess we'll go 4. Fine, we'll go 4 times 15. That actually works. Fine. You want to use numbers at work? We'll do numbers at work. Fine. We won't just pick ones that don't. 4 times 15 is 60. 2 roots 15. Sure. That actually works. See, I was just trying to test to see if you were paying attention or something. Sure. How about root 30? Any perfect squares that go into 30?
Yes.
Other than 1?
8, 4. 9.
No. 9 doesn't go into 30. 4 doesn't go into 30.
1.
1 does. 1 doesn't help us, though.
Then why would we write them?
This is what's called not. This is already in simplest form. There are no perfect square factors that go into here. So root 30 is your best bet. Sometimes we can't simplify. Sometimes you can try and then screw it up like I did in part B. Go from there. If there's division, same as it's pretty much the same as multiplying. We break this into say 2 parts, about like root of 18 over root of 25, and then simplify those. Let's do, if you haven't already, get D, E, and F taken care of quickly. Either way, we get there. These are all 6 examples of just when we have to take square roots and nothing really major. Same simplifying radicals. How about if we get some trickier things here? Like 2 over square root of 3. Well, this isn't violating the perfect square thing. There's no perfect squares underneath the square root. Unfortunately, there is a square root in the denominator, which is bad. Can't have that. So, does anyone remember our strategy for getting square roots out of the denominator? Multiply it by something. Not by a reciprocal. We want to multiply it by something, and since we want to keep this expression the same, it better be multiplied by 1. So we better multiply whatever's on the bottom, we multiply on top. Well, what are we going to multiply by? What's the square root of 3 times the square root of 3?
Square root of
What's another way to write square root something times itself? Squared. So this is the square root of 3 squared.
Oh my god.
Relationship between square root and squared, those are called inverses. And they kind of cancel each other out. So you get whatever's underneath. So if you multiply square root by itself, you get just whatever was underneath of it. Right? Because square root says what times itself is 3. Well, if you multiply that thing by itself, you should get just whatever's there. You get whatever's underneath. If you multiply square root by itself, you basically eliminate the square roots. So if we multiply root 3 by root 3, what's going to be on the bottom here? What's square root of 3 times the square root of 3? Okay, so then what do we now have on top? 2 square roots of 3. Are there any square roots in the denominator anymore? Are there perfect squares underneath the square root? No. That would be our simplest form. Nine over root 28. Let's start, make life easiest for ourselves, and start by simplifying this before we try to simplify this if at all possible before we start trying to do this trick. So can we simplify root of 28? Is there a perfect square that goes into 28? Yeah, 4 does. So this could be written as what? 9 over square root of 4 times 7. 4 times 7 is 28. And what's this simplify too. Okay. We have no more perfect squares under here, but we do have a square root in the denominator. So we have to multiply this by something to make sure we don't have that anymore. What do we want to multiply by? 7. Just trying to confuse you. Doing my best. I just like the number 3, I guess. What do we want to multiply the bottom by? What's the square root of 7 times square root of 7? 7. So this thing should be the same as, this is the same as what? 9 roots of 7 over 2 times 7. Root 7 times root 7 is the whole number 7. And how should we finish this? Nine roots of 7 over 14. There's nothing really in here to simplify anymore. You'd be done. All right, last one. Last one of these guys. 27 over 50. Does that reduce at all? Beforehand, maybe we'll get lucky. Does it reduce at all? Is there a number that goes into 27 and into 50? I don't think so. 2 and 5 go into this. 3 goes into that. I don't think so. So we start by, I bet you we can simplify each of those individually though. I bet you there's perfect squares going to each top and bottom. Namely 9 and 25. So we simplify it's root 27 to root 9 times 3, and 50 into root 25 times 2. 25 times 2. This means we get what? 3 roots of 3 over 5 roots of 2. Is this good? Is this done? If not, what do we need to still do? What needs to still happen? We're going to get rid of this square root. So what are we going to multiply by? Okay, so this is what? 3 roots of 3 over 5 roots of 2. And we're going to multiply by 2 over 2. Great. What is this? What's 5 times root 2 times root 2? 5 times 2, which is 10. Okay. 3 times root 3 times root 2 is what? Three roots of 6 over 10. The geometric mean between two numbers, it's another way to look at an average. Specifically, the geometric mean is the following. The geometric mean you get by multiplying the numbers and finding the square root. So I want to ask you to find the geometric mean of two numbers, take the numbers, multiply them together, and then find their square root. Another way to solve that, another way to do the same thing is to set up a proportion, which is probably going to be a little more useful to us, the proportion way to solve this, than just this formula thing. Proportion being, if I want to find the geometric mean of A and B, I'll set the following proportion. I'll say A over the geometric mean is equal to the geometric mean over the second number, and solve this proportion. How do you solve a proportion? Cross multiply. So if I want to find the geometric mean of two numbers A and B, say A over the geometric mean is equal to the geometric mean over B. Cross multiply, and hey, what do you get? You get multiply the numbers equals x squared. So then square root. You get the same thing as this like formula method. But the proportion, we're going to be setting up and solving these proportions in section 7.3 quite a bit. So it might be a good idea to get practice with the proportion method. So if I want to find the geometric mean between these two numbers, I could say 2 over my geometric mean is equal to the geometric mean over 50. Cross multiply and solve. We get x squared equals 100. The geometric mean, therefore, is the square root of 100, which is 10. Multiply, cross multiply, and square root. Between 4 and 36, again, you can set a proportion. 4 over x equals x over 36, where x is the geometric mean. And we get what? X squared equals 144. The geometric mean between these two numbers is 12. How about between 3 and 8? Three over x equals x over 8. X squared equals 24. X is the square root of 24. Oh, simplest radical form. How do I simplify that? The largest perfect square that goes into the 624 here. It's 4, correct? The geometric mean of 3 and 8 would be 2 square roots of 6. I'll do D, and the last two will be for you. Geometric mean of 9 and 18. Oh boy, 1 over 18, excuse me. Boy, the proportion method is going to be a little bit rougher. How about we just go right to the formula? What was the formula for a geometric mean?
X over 4A.
Okay, that would be the proportion way. So if I did this, that gives me, if I solve this, I get what? X is equal to the square root of A times B. There's A and B. So then what do I get? The geometric mean is then the square root of 9 times 1/18. What's 9 times 1/18? 0.5. How about as a fraction? It's 9 over 18. 9 divided by 18 is 1/2. Is this good to go? What's wrong with this? How about we rewrite this? I'll work up. How about square root of 1 over square root of 2? What's the square root of 1? Okay, so then what should our trick be to get this radical out of the denominator? What do you multiply by? So then what's our answer? Root of 2 over